All right, so in this example here, we're going back to that box on a horizontal surface, and we're going to calculate the work done by all forces that act on this box as it slides across the floor. Okay, so I've specified a couple values here. The mass of the box is 5 kilograms. There's an external applied force by whoever, right? There's an applied force of 150 newtons. The coefficient of friction, in this case, kinetic friction, because let's assume this force overcomes the static frictional force, right? The maximum static frictional force. So I should write this as mu k. And it slides a distance of 7 meters across the floor. It's a long way, okay? So we can mark that if you want to. Something like that, right? 7 meters. We'll call that D right there. All right. So let's draw all of the forces on this box. All right. Let's do it in blue here. So what forces are at play? Well, we have the applied force. I haven't told you what direction that applied force is acting in. Turns out it's acting exactly to the right. So that's our applied force F. And what else do we have? Well, as the box slides, again, we're assuming it automatically overcomes Fs max. So as it's sliding, there's a frictional force trying to oppose that motion. So that points left. So we can call that Fk or F sub F if you want to, the frictional force there. And it's resting on that surface. So we have the force of the surface on the box, right? The normal force, and of course the gravitational force on the box pulling it down. So Fg or of course mg. So let's go through these and calculate the work done using the equation described in the previous video. Okay? Remember, the displacement is always here. We have, I'm going to translate. That's our displacement vector, d, right? It starts here, ends there. So that does not change, right? Regardless of what forces, what force vectors are on it, that displacement does not change. So let's see what we have. The first work we can do, let's do the applied force. So the work done by the applied force. So F dotted with the displacement d, right? This is always the work equation. Again, it's the relationship between a force and the object's displacement, okay? So because this force, the applied force, is parallel to the displacement, that force will do the maximum work, okay? In other words, that force changes this object's energy the most. So the magnitude of that was 150, and the displacement magnitude was 7. And don't forget about the cosine. Cosine of the angle in between, well, that's 0. So that's just 1. Okay, so this equals 1,050 joules. Okay. Next, the work done by, let's do the normal force. Right, so that's the work done by F in. The normal force here, dotted with the displacement. Well, normal force is pointing directly up, and that's perpendicular to, in red, the displacement. So even though we can figure out the magnitude, doesn't matter. That's just mg, right? It doesn't matter because the angle is 90. So you don't even have to do that if you don't want to, but let's see, mass is 5, 9.81. And now what makes it 0 is that it has a perpendicular angle, right? So therefore that work is 0. And it should make sense. A 0 work means that no component of that force is in the direction of the displacement, right? Totally useless. Next, let's keep going around. We have the force of friction now. All right. So notice this is directly opposite to displacement. And so this will have to be a negative work done. This will come into play later on in the chapters, okay? This is very important here. It still does work, right? It's just not a positive work. So the force of friction is equal to, let's see here, F, okay, equal to mu K times F in, and the normal force is equal to mg, right? So we have the coefficient 0.25 times mg, the mass is 5, 9.81, and now the displacement, which was 7, and cosine of the angle in between, well, the force is that way, displacement is this way. They are anti-parallel, in other words, an angle of 180. So that means we have a value now of negative, it should be 85.7 or so. Yeah, 85.7 joules. Okay, it still does work, right? Because it's still a force applied on that object, right? It just is not responsible for moving the object across that distance. And then lastly, the work done by gravity. And so similar to the normal force, these are perpendicular, and so this is 0. Cosine, negative 90, positive 90, doesn't matter. 0. Okay? So now we can calculate the total work done. The total work done is just the sum of that plus negative 85. And so if you were to do that, the total work, oh, what did I have? Oh, I actually didn't have a total work value. It's left as an exercise to the viewer to find the total work done. Right? It should be about, what is that, 965 or so? Right, about 964.3 joules. Okay, but this video should have hopefully showed you how to calculate the work done by all forces on an object that moves through some displacement d. Okay, sometimes forces do positive work, sometimes forces do negative work. All right, thanks for watching.